Hello, I'm Jeff Young with the Arm HPC Users Group, and I'm happy to be here today with Roxana Rusitoru, who is going to present about deep learning with Arm SVE. Roxana is a staff engineer at Arm. She's been part of many different HPC projects, including Mont Blanc 1, 2, and 3. Most recently, she's done research on SVE optimizations, application porting, and specifically for this talk, doing machine learning with Arm SVE. Thanks for being with us, Roxana.
Hi, Jeff. Thank you very much for the invitation and for the kind introduction. So yes, today I'll be telling you about deep learning with Arm SVE. And my slides work. So I'll start with kind of the first disclaimer. I am a sort of an HML, aka HPC person. As you can tell, I'm amazing at drawing, but in part, I've actually spent the better part of my last decade in ARM working on HPC within ARM research specifically. And I've worked on everything from application optimization to kernel development to simulation infrastructure and next generation architectures. And now I do ML. And I'm actually looking after kind of ML on CPUs. So how this whole thing started is this year, Supercomputer Fugaku came out. It's an amazing machine, and obviously you want to train large networks on this, but it's not, this is a lot more than just a simple machine. And some of the workloads that, for example, are running today on it, I mean, I'm saying this is just a subset, are a lot of obviously coronavirus treatment and simulations around, wearing masks, airflow, virus transmission, etc. And as you've seen today, in the news, I'm sure you've stumbled upon this. Quite a lot of them also use machine learning. There was one I remember around. I don't think that this was run on the Fugaku, but there were some simulations being run that helped identify the right proteins for scientists and then narrow down from thousands to a small subset. So they can be very impactful. And kind of going and digging a little bit down into what makes D64FX special in a way is actually, it's a 48 core processor with 4 assistant cores, but it's got SVE. And in addition to that, it's got 2 pipelines, 512 bits, so it's got fairly wide SVE, and it's got a wide range of precisions available from, all the way down to FP16 and int8, which are kind of important for machine learning applications. And in addition to that, it has a tremendous amount of memory bandwidth. It's got HBM2 stacks, and its peak bandwidth is a terabyte a second, which is a wonderfully high number. So let's dig down a little bit into SVE and what it is. I'm sure many of you have seen this before, but in case you haven't, this is like a kind of 2-minute introduction. So first of all, SVE is a new vector extension that came after Advanced SIMD, also known as ARM Neon, and it's added features needed for new markets, aka think HPC, machine learning, and not just things like gather loads and scatter stores, per lane predication, and longer vectors. There are a few key features that make SVE different. So first of all, there is no preferred vector length. The vector length is a hardware choice, ranging from the standard 128-bit, like for example, like Neon, all the way to 2048 bits in increments of 128. And it now promotes a new kind of programming, which is a vector length agnostic programming, which adjusts dynamically to the available vector length. So your assembly, the actual assembly instructions, do not have the concept of vector length. They are, an add is an add. It doesn't matter if it's 512-bit or 2048. The operations are agnostic. SVE is not an extension of the advanced SIMD or Neon. It is a separate optional extension that comes with this new set of instruction encodings. And whilst the initial focus was HPC and general purpose server, and actually not media and image processing, kind of DSP style instructions in Neon are in Neon. In addition to that, SVE kind of begins to tackle some traditional barriers to auto-vectorization. So first of all, we've got very low overhead versus scalar code to encourage opportunistic vectorization. And there are other things like, the software boundary speculative vectorization of uncounted loops So we can actually now kind of manage to vectorize across, for example, while loops. And we can extract obviously more data level parallelism from existing source code as a result of this. So why vector length agnostic? There are a couple of advantages and disadvantages to the approach. The main kind of pros are you can fit into the 32-bit fixed with A64 instruction set encoding all of the instructions. You do not need to add more instructions every single time you increase the vector length, and especially across an ecosystem where every partner can choose to implement, for example, if they have an architectural license, a an implementation suitable for say somebody may say that the for the workloads 1024 is a perfect number. Some of them may say actually, you know what, 128-bit is a wonderful size choice. You wouldn't want to have separate instructions and have to report the code across the different, when I say report, I mean, you recompile fully to get different instructions to do this. It's a very cumbersome task. So this way, with a single kind of agnostic instruction set, you can much more seamlessly apply all the existing binaries between implementations. So I mean hardware implementations. It's also future proofs it, of course, because again you don't need instruction sets. Sorry, when the vector length increases, and also again the code automatically scales to the whole vector length. You don't need to recompile, no need to rewrite hand-coded SVE assembler or intrinsics, none of that. It kind of just works. I will now, obviously, just because this is where kind of the challenges kind of start as well. So just because the code will work, it does not mean necessarily will run as optimally because to remember, SVE is an architectural extension. It's not a microarchitectural implementation. So obviously there are differences between the various implementations. So you're not always guaranteed that just because a code ran very optimally on one platform, it will just automatically run optimally on a different platform simply because it just uses SVE. There are other microarchitectural features like the memory bandwidth, for example, or not even, sorry, that's a system architecture feature, but there are other features that will obviously affect this as well. And also in addition to that, programmers and compilers do have to think differently about factorization. A lot of codes out there are very kind of have very baked in um, notions about you've got to have the 512 or there's kind of the fixed size mentality. So this is a growing opportunity. And obviously, different vector lengths can actually expose latent bugs. Stack layout changes may expose stack overflowing bugs. And it's difficult to validate, obviously, at all these, the 16 vector lengths. Obviously, there are a few kind of really common ones, like, say 128, 256, 512, maybe even 1024. But we understand that, obviously, this is a bit different. So there needs to be more thought going into the software development process here. But let me tell you about some of the other features of SVE. So I already mentioned it's got getter loads and scatter stores, which is kind of a fairly self-explanatory feature. Per lane predication, so you can actually operate on the individual lanes of the vector, and you've got a predicate register that controls the operations. And also we have predicate-driven loop control and management. So you can actually eliminate your traditional kind of loop head or tail and other overheads that kind of you have to use normally when you process partial vectors. In this case, you just set a predicate, and that's it. And also the things like vector partitioning for software managed calculation. So we now have a first fold vector load instructions that can actually allow to do vector accesses to cross into invalid pages. But as soon as it faults, obviously it masks the predicate register, so you don't actually perform any bad loads that you shouldn't have access to. And obviously we also extend kind of floating point and bitwise horizontal reductions for in order or tree based floating point sums and trading off repeatability versus performance. So let's kind of go back to the software. I've spoken kind of a bit about SVE and the value it adds and some of its features, but looking at the software and the training stack, because we want to talk about actually doing machine learning training in this case, there is actually a wide variety of software and actually a wide variety of platforms. The ML software stack is kind of or AR64 and or SVE. To be very clear, not all of these tools available here will work on SVE out of the box. So everything is being ported at the moment, as far as I can tell. But not necessarily all of them will be in kind of perfect shape, most optimized code ever, because as we just got, as SV platforms this year. So, there's obviously still more development to be done, but a lot has already been this tremendous amount of tooling and libraries out there already. Also, likewise, not all the platforms that are listed in kind of the hardware list have SV or have all the architectural features listed here. This is just an overall wider view of the available architectural features for ML training or ML in general. Uh, some of the AI64 kind of platforms and some of the things. So I'll go briefly through them. So for available frameworks, popular ones such as TensorFlow, PyTorch, Caffe, we already have container images, like Docker container images and build recipes to kind of help developers get along if, get started sooner, or users, not just developers. And already popular ML frameworks support ARM as a first-class citizen. In addition to that, we have ML libraries such as 1DNN, Eigen, ARMPL, and ARMCL available as well. And this is not just us. There's a tremendous amount of effort and development that's also gone throughout the entire ARM ecosystem. This is not just ARM, contributing some of these. For example, Recon or Fujitsu have also posted lots of developments online, also on GitHub, open source. So please do check out some of the work as well. And we already have the debuggers you're very used to. ARM4, DDT and map and profilers are obviously available and working. We also have a selection of training benchmarks. I put kind of the most popular one being MLPerf training. There's also obviously MLPerf HPC. You know what you kind of your preferences are, so that's kind of up to the user. And in terms of architectural features, we've got .product support, we've got SVE, and actually there's SVE2 as well. Even though, to be clear, none of the implementations listed support SVE2 at the moment. I mean, we just got SVE. Um, there will be quite a number of years probably before we'll see the first SVE2 one. And we also have things like int8, bflow16, fp16, fp32, which are data types pretty much necessary for machine learning. And we also have added a matrix multiplication extension as well. And we've got a very wide range of hardware. We've got the ARM Neoverse platforms, the N1, the V1, Ampere Ultra, Fujitsu A64FX, and many more platforms as well. So why actually look at on CPU ML? Because I've been talking about, SVE and some of the software ecosystem available and some of the other architectural features. But why actually look at CPU on CPU ML? So for starters, it is you have a great range of flexibility. It can, especially if you have already, for example, CPU code, it's very easy to integrate, and you can run a wide variety of models and um, of algorithms are very, very easily. In addition to this, it's very easy to program. It's kind of safe to say that a lot of the people out there have a tremendous amount of experience programming on CPUs and integrating already with existing code. But also, we already have added ML processing kind of specific features towards this as well, and a kind of a short list on the right. So we've got, obviously, again, the short version is architecture and microarchitecture features, the .product instructions, the matrix multiplication ones, SV vector length. Oh, so the SV vector length is the microarchitecture feature, and again, architecture bflow16. And in brackets, you have the architectural version, the binary architectural version, where the feature was introduced. So yes. And in terms of frameworks, I mean, this is just, I'm sure this is not actually a fully complete list, but ARM is already very heavily involved, for example, with TensorFlow and dbench, and We've got, some of the other frameworks like Torch and Cafe are community maintained, but it's also going to speak to the ARM ecosystem and the breadth of work that's there to do and the active involvement of everybody into this. And to kind of ease some searching, I've put some Docker builds for popular ML frameworks. I put the links to them here and some details, community blog posts as well, in case you want to check these out. And overall, ML training on ARM-based systems, in a way, it's Supercomputer Fugaku and Arm SVE are just the beginning. If you think about doing training on a machine like this and using SVE, they are just one implementation and one kind of design point. We already have a versatile architecture that's enriched with ML features, and we have a diverse selection of ARM-based implementations, as you've seen. And there's already obviously always there a freedom to design fit for purpose hardware if that's something that you're interested in. And we have a vast software ecosystem that can that can support this as well, and a very large partner base, all working towards a common goal. And I've just kind of put here also a few resources, but I've got by the way, just gonna shout out to John Lundford's hackathon coming up soon, and also porting and a few guys porting optimizing HPC application from SVE and an SVE Neon coding compared guide as well. Yeah, to be clear, I mean this is just the beginning, and also in case you're wondering, we can also do a lot of inference. There are accelerators for inference as well, and there's a whole software stack for that as well. So this is not just I just kind of focus on training in this talk. And thank you very much.
Okay, thank you, Roxana. That was a great talk. It's very exciting to see all these new developments, especially in the software space. And I'm sure we'll see some more interesting hardware implementations that go along with that. For all our viewers, thank you for watching. I want to point out that we have panels November 9th, which will be recorded. They'll be on a Zoom link. It's not on the slides here, obviously, because this is run in part by AHUG. But if you go to our website, a-hug.org, there's an Eventbrite link there that you can sign up for. And Roxana will actually be part of the on-site experiences panel, which will be held at 9 a.m. Pacific Standard Time. So thank you, Roxana. We'll look forward to talking with you more then.
Thank you, Jeff.